Okay, I'm going to just jump in here to assembly language programming here, but before I do that I need to talk a little bit about the internal structure here, and probably the easiest way to do that let's see. No, this is not going to be the place. Okay, well, we'll just jump in here and we'll go ahead and get into. This is where we left off here. Right there. Let's just. Okay, let me just go ahead and start from here, and then we'll have to discuss a few things here. Okay, I'm going to start talking a little bit about assembly language programming there using the 8051. And keep in mind that the 8051, we're going to be, when we start looking at assembly language programming, the internal architecture that we're going to use is relatively simple. We're only going to treat this as having two registers, A, B, and then R0 through R7. Those are the registers we're going to deal with at first. Now, R0 through R7 is a little complicated, and I want to keep it simple for right now. Because actually, R0 through R7 are actually stored inside the static RAM on the chip, and there's 4 banks of R0 through R7. We're just going to use bank 0 right there. So we're just going to treat them as 8 registers. So we're going to look at our code relatively straightforward, and I'm going to go through 2 sets of slides that covers the same basic material, but I want to kind of get there, and they cover it a little bit differently right there. So our registers used to store information temporarily. It's a byte to be processed or an address point of data to be fetched. The vast majority of the 8051 registers are 8-bit registers, and we're only going to use one data type when we do most of our programming. So we're going to be looking at bytes, 8 bits, right there. So a byte, as you recall, is 8 bits, right there. So we look at this right here. The basic way we look at this is a byte is we've got digits D7 through D0. Each one of these is a 1 or a 0, right there, and they can be broken into right there. Some registers can be bit addressed, some can be only byte addressed, right there, and depending on there. For today, I'm only going to talk about 8-bit registers right there. So here, this is the basic set that I was looking for right here. Is that when we look at our most commonly used registers on the 8085, the accumulator, which is called the A register, that's the most important one, because if we do any add, multiply, divide, the result's going to be stored in the accumulator, and sometimes in B. So we have 2 registers that we use predominantly. They're A and B, and then we've got also R0 through R7. So those are the registers. This is the programming model we're going to use for today. We also have 2 other 16-bit registers right here. These 2 are 16-bit right here, and right there, and that's the data pointer, and that's got 2. It's actually two 8-bit registers, data pointer high and data pointer low. And the reason it needs to be 16 bits is because we can address up to 64K of memory with this processor. And then we've got the program counter. The program counter we normally do not use when we do programming, right there. It keeps track of where we're at in the program, and we will look at it to see where we're at in our program when we're debugging, but we normally do not write or read from the program counter. So if we do jumps and calls and interrupts, they will all change the program counter, but we don't write to the program counter or read it directly. So that the data pointer we may or may not, the data pointer we will write to from time to time, right there, and we'll use it when we do indirect addressing, right there. So when we look at this right here, this is the simplest instruction. It's called a move instruction. Now, in reality, it doesn't move the data, it copies the data. So we have multiple ways of moving data around. If we put a number sign in front like this, the number sign, that means immediate data. And my other set of slides actually does a better job of going through these, so I'm going to go to them later after I do that there. But what this does is it moves into A the number 55 right there. The next one copies whatever is in A to R0. So if we run this code, and I didn't bring a board, and I told them to take the boards back, so I'm not going to go through this on a board right there. But we'll do it next Monday. Now Wednesday, let's see, this class meets what day? Monday, Tuesday. What? So we meet again on Wednesday. So I'll bring a board to go through some samples. And the next Monday we'll do 2 labs. We'll do the labs right there. So, well, we don't meet on Wednesday. We meet tomorrow, right? Yeah, because I remember I got in trouble last week because I kept saying that we didn't have class on Wednesday, and everyone kept trying to tell me that this class is not scheduled for Wednesday. So, up there. And I'll be honest, I've been teaching for 30 years, and then if you add all the years that I was a student beforehand, I've been around the university systems in the U.S. for about, I'm going to say almost 40 years, 35 years plus. And in the U.S., there is no such thing as a Monday, Tuesday class. Everything is Monday, Wednesday, Friday, or Tuesday, Thursday. Or if it's a 5-hour class, it might be Monday, Tuesday, Wednesday, Thursday, Monday, Tuesday, Thursday, Friday. But there is no such thing as a Monday, Tuesday class in the U.S. That's why I'm so easily confused. That's there. So, all right, getting back to this little piece of code, and this is what an assembly language program might look like. Now, this is not a this particular program doesn't necessarily do anything super great other than the fact that you might see something like this on the final exam, and you might be asked to, what is the contents of what register at the end of this code. So the first thing we do is this first instruction here moves the number 55 into A. And now if that number sign was not there, it would look at memory location 55 and move that data, whatever's stored in memory location 55. The default is a memory location. The number sign says that it's going to be immediate data right there. And we'll look at there. So number sign means immediate data right there. In other words, we don't look at any memory locations. We don't look at anything. We just take the number 55 and we put it into A right there. The next one says take whatever is in A and move that to R0 right there. So if we go through and I'm just going to put it here, A, B, R0, R1, R2, R3, R4, and I think I can stop there because actually this program only goes up to R3. So it's going to put into A the number 55 right there. Then the next line of code moves 55 to there. Now, this is a little bit different because it copies this direction. It says move into A the number 55. The normal way that somebody might read this is move 55 to A, and they'll want to write it move number 55 to A. You can't do that. First off, the reason that you can't do that is you can't move the accumulator into a number right there. But the designation is first, and then it's the data. So everything moves this direction. It's backwards from normal thinking right there. Normally, you would look at an instruction there and you would say, move A into 55, right there. You can't. No. It's move into A the number 55. The data moves this way, right there. Move into R0 A. Move into R1 A. Move A into R2. Move 95 into R3, right there. And I wrote 93 right there. So basically all the move instruction does is it just moves data from one place to another. Right there. It's a relatively straightforward. There's different variations of that, and we'll see those later. This one here, all we're doing is moving the number 55 into a register, and we're just moving A into all the registers. We're moving the number 95 into a register. We're moving R3 into A, so R3 will now contain 95 at the end of this code right there. So at the end of this here, A is going to be equal to 95 right there. So again, what we're looking at here is if we have a letter as our first number there in an immediate data, or anytime we're talking about a number and it starts with a letter, you would always precede it with a 0 right there. That means that I'm going to move into R5 the number F9. The 0, it can't be moved there, but that just tells the assembler that it's a number. It sees that F, it gets confused easily. Right there. If I just had number F9, it gets confused. Right there. And of course you put an H at the end of it. If you don't put the H in there, that's illegal, because you have to put the 0 there to tell it that it's a number, otherwise it doesn't know. And if you don't put the H, it's going to assume decimal. Right there. So if you do, for example, move a number 23 and move a number 23 hex are different instructions. This moves the decimal number 23, base 10. This moves base 16. So you have to put the H at the end, otherwise it assumes base 16 right there. Some compilers and some program that there will use 0x to denote hex right there. If you worked with C, you would use normally 0x right there. We're working with assembly language, so we're using the H at the end. And then you can use the B at the end too as well, for if you want to do binary. So you can put the data in either decimal, hex, or binary right there. That's how you can write the data there. So I could have the instruction move a what did I do here? I totally got myself lost here. I'm completely, now where did I go here? I'm way down in the book here. I'm in chapter, 15 here? Let's go back. Oh, I'm way down in slide number 500. Okay, let me get back to where I was at here. Okay. All right, what I was saying there last right there is that you could write you could write it binary as well, that there. Typically, we don't write binary right there. So, now, keep in mind a few of the rules here that this slide kind of addresses here. One is you have to have the number sign there to denote that it's immediate data. Otherwise, it assumes that you're going to move the contents of memory location 23 hex into A. That's different than the number 23 hex. Also remember, if you don't have the hex or the H for hex, it moves the number 23 decimal, which is 17 hexadecimal right there. I'm guessing that it's 17 right there, but that sounds about right. You take 16 off there. So again, the H is important. The other thing that's important is that if you start with a letter, you need to have a 0 in front of it right there. So if the values 0 to F are moved into 8-bit registers, the rest are assumed to be zeros. So in other words, if I have number 5, that's going to put in 0, 0, 0, 0, 1, 0, 1 right there is what it's going to put in there. It's going to put 0, 5. So if you put number sign 5, it's going to assume it's 0, 5 right there. In this particular case, 5 decimal and 5 hex are the same right there. So normally we would put this move a number sign 0, 5 hex would be the more clear way to write that, where you don't. Now, if you do this command is wrong because A is only 8 bits and this is a 2, 3. That is a 12-bit number. That's 3 digits. There, 7F2 requires more than 1 byte. It requires more than that number is too large, right there. So you've got the problem there is that you're trying to move into A 3 hex digits, and 3 hex digits takes 12 bytes. Remember, 1 hex digit takes 4 bytes. We have, one hex digit takes 4 bits, which is 1 nibble. So 2 hex digits equals 1 byte. You know, we get our bytes and our nibbles here and bits all straight here, right there. This number right here is 3 hex digits. It means it takes 12 bits. We have 8 bits available. That's too big of a number to put into that there. So you can't do that. So you can put in the number sign 0F2. You can put in the number sign 7F, but you can't put in number sign 7F2. Now, if you leave the number sign out, then it's going to go to memory location 7F2. And you may or may not have that right there, depending on that there. So, okay. The next command in our set of instructions is the add command. The add command, again, typically whenever you're going to do the add command, you normally use A, but you can use any of the registers for A. That there. This right here, it says that we're going to move A in here, and notice that here we're always using the A. It's much more efficient, and depending on the processor, you normally would use the add command tells to add the source to register A and put the result in A right there. So A is equal to whatever A was plus whatever we tell it to add to is what we're doing. So in other words, if we look at our code, we're moving 25 hex right there. So A contains 25. We're moving the number 34 to R2, 34 hex, and we're just going to add a R0 right there. Or no, R2, excuse me, R2. So A was 25, so it's equal to 25 plus 32. These are in hex numbers, so that's going to be 57 hex right there. And this is where I'll go through this with the board later, right there. So the add right there. We have the option of using immediate with the add as well. We don't have to use registers. There are many ways to write the program. You can do that there. They're just showing that if we're wanting to add 25 to 34, we could do it this way, where we put 25 in A and 34 in R2, and we add R2 to A. Or we could move 25 into A and just add the 34 right there. So you have multiple ways of doing that right there. And I said 32, that should be 34, so that's going to be 59 hex right there. So again, we've got the add instruction. So we got move and we've got add right there. So, okay, this just gets into a little bit more discussion. Early days of programming consists of zeros and ones, slow and tedious. That's there. We're going to be doing assembly language. It's a low-level language right there. My first programming I did in opcodes. That's there. This is actually getting into a little bit more detail of the structure right here. That was just some examples there. But as we go through here, assembly language, hold on, let me make sure I didn't. Yeah, okay. All right. That there. For some reason, it seems like I'm skipping around here. Okay. Assembly language includes the instruction itself. Move or add is what's called the mnemonic. That's the instruction itself. Followed by one or two operands. You can have more than some instructions have no operands. Now, in other words, there's nothing there. So after it, an simple one of that might be a no-op, which is simply does nothing right there. There might be some instructions that have one operand, and we'll see some of those up there. So an assembly language instructions includes instructions, and it also includes directives. We'll look at some example programs that has both right there. One example, when we did Blinky, there was one where we set a S bit equal to a particular value right there. So here is a example of a short little program right there that simply says we have the first instruction that says org right there, start location that there. Now normally org just simply says that's where we want it to place it in memory. Now most of our programs, if we do an org, the first thing we're going to do is have a long jump to start right there, or to main. Right there. This is actually a program you wouldn't use because the first memory locations are used up for the interrupt vector table. We haven't talked about that there. So, but again, what we're looking at here is org is a directive. It's not really code. It's just telling the linker, actually in this particular case, that's where we want the code to be in memory. Right there. Org right there. Our mnemonics are move and add. Those will actually generate instructions that have opcodes. We're not going to worry about opcodes so much in this class. When I first started programming, we had to look up the opcodes by hand, and we would enter the programs. Fortunately, we don't have to do that there. And then we also have comments right there. A comment is anything after the semicolon. And comments are very good, especially for assembly language program, is it kind of helps you remember what your brain was thinking when you wrote the code. That's there. Assembly language code is very cryptic when you read it after the fact. What in the world is this supposed to do? Even when you write it, sometimes it seems very cryptic. That's there. Other languages such as C, Pascal, Fortran, BASIC, you can kind of read the code and get an idea what's going on, because the instructions are a little clearer, they do a little bit more. But in assembly language instructions, you're writing at the lowest possible level. You're writing in the code is at the lowest possible set of instructions, right there. It's kind of like the ladies might relate better to this than the guys, but the guys will relate to another example. If you have a recipe right there and you want to cook, and and you want to make a cake, and it says, mix 3 eggs, right there. That's, you know what that means, right? You go and you get 3 eggs out of the refrigerator or the countertop, you break them open, put them in a mixing bowl, and you whisk them, right? Right there. Well, if you're writing assembly language code, you don't say mix 3 eggs. You say open refrigerator, pick out 3 eggs, repeat, or pick out 1 egg, repeat 3 times, break egg, repeat 3 times, pick up mixer, mix. That's there. Yeah, it's very, very low level. I mean, the instructions are, that's there. I want to add 2 numbers together. I just can't say add, x is equal to y, a plus b, right? No. I have to move the first number into the accumulator, move the second number into a register, add the 2 of those numbers together, and then store the result someplace else. That's there. It's very, very tedious. That's there. If, for example, if I want to write a program in C to add 2 numbers together, I can do a scanf right there, and I'm just going to say num1 right there, and then you'd have the %I and blah 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 blah. I'm not going to worry about the syntax here. Scanf num2 right there, and result equals num1 plus num2, right? Right there. And that's what there. The assembly language, we just saw that we can't do that, right? We have to move num1 from someplace. Now, we may have to call a function that's going to read the keyboard if we're writing for a desktop computer. So we may have to say get key, which goes through a whole process. Getting num1 is not as simple as just a scanf. Right there. So that's why assembly language programming is the lowest form of programming, but it's the way that you understand how the processor works the best. That's there. Once you learn how to program in assembly language, then you can start troubleshooting problems when you write them in a high-level language. That's there. Believe me, I do not write very many assembly language programs that do real work. I do not write assembly language programs to do real work because it's too tedious, too long, too grueling, too many places mistakes. But I often have had to sit down and debug assembly language programs that don't work right, and then I have to look back at the original C and see why the compiler didn't compile it correctly. That there, and I may have to fix that there. So there's a need to understand assembly language program, but there isn't a need to write a lot in assembly language program in the real world. At one time there was. Microsoft DOS, written back in the early 1980s, was written all in assembly language. Right there. The original C compilers were written all in assembly language. Right there. So nowadays we use, almost everything's written with either. If it's for an Android device, it's going to be written in Java. If it's Apple, I don't remember what the programming language. I think it's C, because Apple is based on Linux, right there, Unix. So right there. So again, we're looking at this very low-level code right there. So, okay, the processes we're going to go to is we're going to use the editor. Now, in our case, the editor we're going to be using is, we're going to ignore that. We just use the editor that comes with the IDE. So back at the time this book was written, you would normally use a standard text editor. This book is an older book, and you might use something like WordStar or Edit or something, one of the old ASCII. Notepad was one that you could use, but it had to produce an ASCII text file right there. Word does not produce an ASCII text file. Word produces a doc. You can't compile. You can use Word actually and tell it to save it as an ASCII text file though. But there's better editors right there. Right there. So many editors follow the names. Typically, ours are going to be named .asm right there. So what happens when we write the code? The assembler converts that into machine code, And the assembler produces two files. One is an object file and the other is a list file. The object file we normally don't look at much because we can't read it. The object file is actually used by the linker right there, to create the what we want to call it, the absolute object file that's actually going to create the code that goes down into the board right there. So the linker, this third step, actually allows us to use multiple source files to create a single program right there. In this class, we're going to have one file, one program right there. For many projects that I've done in the real world, one file might be 30, 40 pages, and that would contain, say, all my subroutines for interfacing to a particular sensor. I may have another file that would have all my subroutines that would interface to the database. I would have another subroutine that would do all my hardware drivers. So you might have multiple source files that you would then link into one object, into one final file right there. So, but we're going to the list file is handy, and as it turns out, when we run our assembler, the list file actually we can look at on the screen. We don't have to open the file separately. It shows up on the bottom as our output, and that contains information. If we got syntax errors, it shows where the syntax error is. Makes it easier to debug our program for syntax errors. It doesn't help with runtime errors right there. So, but typically, if you remember the other day, I did that rebuild all button. When I hit the rebuild all, it does the assembly and the link combined. It does both right there. If I go back to that code right there, and let me just kind of go bring up right there. Right there. This is the assembly language code we were using the other day, right? And no, actually, this is a C code. We don't want the C code right there. All right, let's close that. C source. This is for C. Let me C source. Let me go here to okay. All right. This is very much like, matter of fact, this is the program I wanted to run the other day, and I didn't remember where it was at there. Okay, this is a typical assembly language program that we would run our code for. And I'll kind of go through this one here. This is a little different because this doesn't use the timer right there. So we've got some comments now. We include a file here called FC8051F850.inc include. What this file, and this is an assembly language directive right there. What this file does is it tells the compiler or the assembler what the memory location is for port 1. So when I say green LED equates P1.0, it knows what this is. That is defined in this file right there. So that's there. Now again, this is a little bit different right here, and again, our compiler runs a little different than what's described in this textbook that I'm referring to. There it uses org 0 right there. Here, this says that I want to put in the code segment at location 0, this code following right there. So we're setting up in the code segment, we're saying at location 0 we want a long jump to main. And then down here we've got something called blink, and it's in our code segment, and we're using register bank 0 and register bank blink right there. So this here just simply says that it's in the code segment where we don't care. Up here I set C segment at 0, so that tells me I want it in the code segment at location 0. I'm specifying I want this at location 0. Down here, this says that I want this code somewhere. This is code, and I want it in the code memory. I don't care where. We'll let the assembler and the linker decide where to put the code. So this is the way our code's going to look. And this is saying that we want to use register bank 0. Now, I mentioned before that we're using R0 through R7. What I didn't say is the fact that there's 4 different banks, and we can use one of the 4, and we can change those when we want to. So we can have a total of 32 registers. But we're going to, right there. And then this is a label called main. This is where our code is going to start. So when we run our code, right there, it's going to start right here. This is the beginning of my code. It's at location 0, absolute location 0 in memory is a long jump to main. Right there. Now later on we're going to talk about interrupts, and the first part of memory is the interrupt vector table. We haven't talked about interrupts, but a reset is an interrupt. And whenever the reset button is pressed on the microprocessor button board, the microprocessor will go to memory location 0 and start executing code. So location 0 is important. That's where your code starts. That's where it starts going. In this case, it's going to jump to main. Main, we don't know where main is. We have no idea where main is right there. It's somewhere in a segment called blink, and it's going to be using register bank 0. The compiler or the assembler will place this where it's most convenient for it to place it. We don't care where it goes. Right there. Now we've got a few commands here. These commands, all they do is just simply move into particular locations, and we won't talk about this one much this semester, but this is the watchdog timer that just disable it right there. This enables our crossbar, and this allows us to use the output pins right there. This is the logical OR. We're setting a bit to 1 right there is what we're doing, and we'll go through those instructions right here. Here we're clearing the LED, which means we're turning it on. Here we're moving into R7 the number 3. Here we're moving the number 0 into R6 and the number 0 into R5. See? We're just moving those in. And then here we've got a series of nested loops. This command we haven't talked about yet is called decrement and jump not 0. Decrement and jump if not 0. And not 0. See, DJNZ. Decrement, jump not 0. Is what that stands for. And we're going to go through all these commands before the end of the hour right there. So, and we've got these, and we'll go through this program flow in a little bit more detail. This is actually the one I wanted to go through last time. We'll probably go through it, next time a little bit there, because this is the assembly language version. All I wanted to do last time was just basically have you turn on the board and see it blink a light, not have a clue what's going on in the code, and that's the end of the program right there. Because all this command here does is toggle the LED on and off. So this does the same thing as what we did last week, right there. Now let me go back here, and I'm going to jump to the other set of slides right there. right there. And we'll come back to this instruction right there. The dollar sign means we do this. Let me kind of point out here what's going on here. Right there. Since I've opened this can of worms, let's talk about this command a little bit. I move into R5. Right there. We move into R5, the number 0, 0, right? The next command is decrement jump not 0, R5, and we put a dollar sign there. The dollar sign in this case is a little cryptic. It means here. In other words, stay right here. Now, when I take 0, 0 and I subtract 1, I'm left with FF right there. See? That's a little tricky there, but it's going to give me FF there. So I decrement before I do the look for a 0. So this is going to spin around 256 times. Right there is what that's going to do. Is what that that's what these instructions do. All it does is just kill time. Right there. Because I decrement, I started off and I got 0, 0 there. I decrement 1 from it. It's got FF, and I jump, if not 0, back to the same place. That's the number. It's a number. FF. No, it means it's 255 in hex. That's there. If I take my calculator here, if I take my calculator and put it in programmer mode and put it in byte, right there, right? If I take 0 and I subtract 1, I get -1, but look at the byte, the hex for that. FF, that's -1. Right there. I subtract 1 again, I got FE. Right there. So it's a little strange. If you take 0, 0 and subtract 1, you don't get -1, you actually get FF. Right there. And then you subtract 1 again, it's FE. And then you go around until you get to 0, 1, you subtract 1, you get 0, 0. So now you don't jump. Right there. Because remember, our command is decrement and jump, not 0. So this is going to start off, I started off with 0, 0, so it goes to FF, FE, FE, FD, all the way down, we get to 0, 1. Then when I decrement, I got 0, 0. So I'm going to jump if not 0. Well, it is 0, so I don't jump. I go on down to the next instruction. That's there. So I execute this instruction 256 times. Right there. That's very similar to saying for I is equal to 255, I not equal to 0, I minus minus, right there. Something like that right there. Where we're subtracting 1 from it all the time, and as soon as I is equal to 0, it drops out there. And I can't remember if that's right syntax or not. But in basic, it would be for I equals 0 to, or 255 to 0, some code, and next I right there. In other words, all we're doing is we're just doing a loop right there. So as we look at this command, this instruction right here, all these two instructions just simply do that there. Now the next instruction subtracts 1 from R6 and jumps, if not 0, back to R0 and repeats that inner loop again. So now that's going to cause, this is one loop right here. This is the loop. And then this is the outer loop right here. And then this is the, so we've got 3 nested loops is what we've got there. So again, we haven't really got into these commands too much right there. But that's how this code works. And then remember back to what I said about open refrigerator, pick up egg, put in bowl. Pick up egg, put in bowl. We have to do this one little step at a time. We want to kill time. We have to move 0, 0 into a register, subtract 1 from it, and then just keep doing that over and over and over again until we get to 0, and then we repeat it again. That's there. So what we're going to do is the inner loop goes 256 times, the outer loop goes 256 times, and then we control the most outer loop goes 3 times, 4 times. So, okay. I opened the can of worms on this program. Don't get too hung up on this code right yet, because we'll come back and see this. Because I want to go through some commands first here. I'm going to jump over, and I want to kind of go through the instruction set here. As I started going through the instruction set, I've concluded that I want to use these set of slides instead, simply because they're a little bit more clear right there. So that actually does a better job of starting the instruction set. This actually gets into all the various modes of operation right there. So this set of slides covers all the instructions for the 8051 right there. Before we cover that there, this is the same information we had: instruction, destination, source. That's the same thing as I just had a few minutes ago right there. Okay, this goes back to our architecture overview, what it looks like. Again, remember that what's not shown here is R0 through R7 right there. Right there. Okay. So there are 8 modes of addressing. And this is on the final exam. I can tell you that right now, to know the 8 modes of addressing and give an example of each. So this slide right here is one that will show up right there. So register to register, move into A the contents of B right there. Direct means here, notice that we don't have a number sign, we have 30H. That's move to memory location 30 hex. This is 30 hex. That's a memory location. And we're going to move whatever is in A gets moved into that right there. Remember, this is where it's going to go. So whatever is in A gets moved to memory location 30. I know it's a memory location because there's no number sign on it here. So if you see just the number by itself with an H after or without an H, that means that's a memory location. So we're moving from the accumulator to memory location 30 hex. Now sometimes this is hidden. You don't necessarily see that it's a direct. For example, move P1A. That's actually a direct that there. P1, as it turns out, is memory location 90 hex. You don't know that, but I know that. That there. And the reason I know that is because location 90 hex is listed in the special function registers as a location, memory location that means port 1. So as we look at these special function registers, we'll use port 1, but in reality, that file that I told you about, that C8051F850.inc, that file tells the assembler that P1 equals 90 hex right there. That's in that file right there. So as we go through, we'll see that this direct sometimes is hidden. You know, you won't say memory location 30 hex, or 90 hex, but you'll put that there. Same thing as that code that I just had a few minutes ago here. Right here. Move the number 0DE hex into watchdog timer control register. Watchdog timer control register is a memory location. I don't know what memory location it is, but it's listed in the special function register right there. Same thing with XBR2. That's a memory location in the special function registers. The next command is do a logical OR with P1 mode in and P1 mode out. Those are two special function registers. So those are direct memory accesses. These are locations in memory, but they're hidden because they don't have the address. So sometimes this one is hidden in the instruction. You don't recognize it as a direct. Now, indirect, this one is kind of an interesting one. We'll talk a little bit more about this one here, but R0 is an offset right there. In other words, R0 is going to point to a place in memory right there. And we'll not worry so much about that today. But R0, if you see that @ sign, it means it's indirect memory addressing. R0 is acting as a pointer right there. R0 right here contains an address of some type right there, and it's going to point to someplace in memory right here. So it's going to look here to get the address and move that into A, or right there. So that's very handy for situations where you want to do, say, array processing. You would use indirect right there. Right there. So again, the next one is immediate. We already talked about immediate, right? That's with the number sign. That means the number 80 hex right there. These are short jump, long jump, absolute jump, and long jump. Those are all jumps right there. We already looked at the long jump right there. And these have some restrictions to them. I'm not going to get into them today at all. But they're actually memory, they're addressing modes, but they're used for jumps commands. The long jump means it can go anywhere far ahead. I mean, you've got all 64 or 16 bits of the address there. These are you're limited to 127 bytes plus or minus, and I think somewhere 1K plus or minus there. And this one here is move from the code memory into A, whatever is contained in A plus the program counter. So that's another indirect index right there. So these are the ones for today. The ones that you should know are right here. Right here. Those three are the ones that I'm going to be looking at today. This we'll get to later. These are part of the jump commands. We'll talk about those much later. And this we probably won't even get to this semester. Right there. But the immediate constant we will use, the register we will use, the direct we will use. The indirect we will get to later in the course. We won't talk about that today. Right there. So those are our 8 modes of addressing. Now, these are examples of all of those right there. Right here. Move into R0, the contents of A. Now, this refers to, is written in R0, the register bank must be specified beforehand. If you remember that code that I had a few minutes ago, right there, I had right here this using 0. That told me that we're using register bank 0 right there. So normally we would just use 0 right there. So this is an example. All we're doing is we're moving the contents of A into R0. Right there. Direct means, again, this is going back to what I just said a minute ago. Transfer the contents of port 3 to the accumulator. Now, port 3 happens to be an address someplace in the special function register. So it's given its abbreviated name of port 3. But here's how we read port 3. Port 3 happens to be 8 pins on the outside of the processor. So that's how we're reading outside data in. So that's there. Transfer the contents of RAM location 20 to the accumulator right there. So we're reading location 20 in memory, which happens to be actually still inside the special function registers there, but we're going to be reading that there. Now notice it says abbreviated special function names are defined in the header file, and I mentioned we're using the 850 header file there. So some of these are different. Indirect is a little bit different. This mode uses a pointer to hold the effective address. That's there. So that's there. So again, if we're using the memory, internal memory of the 8051, that's limited to 256 bytes. That's there. So if it's 256 bytes, R0 and R1 can be used. If we're using external memory, we would use the MOVEX command, and we could use the data pointer to point to our data. But this contains the address. R0 contains the address of where we want to store our data. Right there. So again, that's useful if we want. Then we can increment R0 and then do our next one. So we can fill up an array of data right there. So again, I'm not going to get into this in much detail right now, but we will see this later right there. This is the external. Now, I don't know if I mentioned to this class or not, but it's a little confusing where the external memory is, but that's there. Immediate, we talked about this right there. The only place you can use a 16-bit is if you're going to go to the data pointer. Right there. That's our only, and I believe the stack pointer too. We can set the stack pointer. 16-bit right there. But again, the number sign means that it's the immediate data. In other words, immediate constant. In other words, that number is fixed there. Relative, this is like what I just had a few minutes ago, only here, instead of doing a decrement jump not 0, this is the same thing here. Decrement A and jump not 0 to go back. Right there. So, and then I can put before this move A 0 0 hex right there, number sign right there. So we move 0 in there, we subtract 1 from 0 0, it gives us FF, and then we jump if not 0 back to go back. We subtract another 1, and this will loop around 256 times. Or we could say, for example, we can put number sign 1E, for example, and it's going to jump that many times back. It doesn't have to be 0 right there. It's just going to be 1 more than the number of times we're going to jump through here. So 0 0 is unique because that's the maximum number of times you're going to loop around. That's 256 times right there. But if you want to put anything other than 0 0, then it's that actual count plus 1 right there. So right there. So again, the key thing here is the location it's got to jump to. It's got to be plus or minus roughly 127 bytes. It's got to be within that same 8-bit range right there. Absolute usually is you're going to give it a call. This is an absolute call, and this is a location right there. Here we're calling a subroutine. A subroutine is like a function in C. We're going to A call, which means it's going to be somewhat far away. Port initialize right there. And that's a function, and at the end of the function there'll be a return. And it'll go back to that there. But this is a function call is what this is, or a subroutine call is what that is. That there. And this is using absolute addressing. It means it's got to be someplace nearby. And then the long jump is a long call, and that can be farther away, much, much farther away. This is a long call. You can also have a long jump. That there. Here a call means we're calling a function which will have a return. A long jump means we just go there. There's no return address. Right there. So those are the three there. And indexing is kind of is relatively complex, but it allows us to store a bunch of data someplace and access it right there. And I'm not going to go through that there. Okay. How are we on time? Right there. I think the next group will probably be a little short because I'll probably just jump right in these slides right here. But I just want to see what our time is here. Oh, we got time right here. Okay. Okay. As we go through here and we look at our 5 different groups of instructions here. These are our building blocks. We've already looked at a couple of these. The arithmetic instructions, logical, data transfer, Boolean variables, and program branching. Arithmetic is add, subtract, multiply, divide. Logical is and or. Data transfers are moves, right there. Boolean is or and, right there. Boolean variable operations, we'll talk about. And branching is jumps and calls and things like that. So here they are. This is all the instructions in the arithmetic category. Right there. A lot of them, right? But we'll notice here that we've got we got the add. In the add, we've got various there. And notice that the adds all have add A. So if we're going to do an add, the result is always stored in the accumulator. So one number is always going to be moved to the accumulator, and then the next one is we can add A to a register, we can add A to a direct memory, we can add A to indirect memory, or we can add A to immediate data. So they're all variations of the same function right there. The next group is also adds, but they use the carry flag. Right there. We're going to have an assignment later on where I'm going to make you add 2 16-bit numbers, and you have to look at the carry flag. Right there. So basically when we look at that, if I'm going to add, for example, F2 to 3, 1, this is going to give me 3. This is going to give me a 2 with a carry out. This is the carry flag. So then when I add the next set of numbers, I would look at the carry flag right there. And we'll do an assignment on that. But what this does is it takes into account adds the carry flag to our result. Now this one doesn't, the carry flag set. The next add command we do, we have an add carry. If the carry flag is set, it adds 1 to the result right there. Right there. So it takes into account the carry flag is what that does. Now we'll see, and we'll do some labs with these, and they'll make more sense once we start doing some labs with them right there. My goal is to do labs almost every week or every other week right there. We just got put behind because of last Wednesday being off right there. So, or last Monday. I don't know how we got that there. Okay, then the subtract's the same thing. We have our subtract. Now all of our subtracts take into account the carry right there. We have 4 subtracts, and the subtracts all work the same. It's A minus whatever the other minus the carry flag. So if we have a borrow, we would subtract that off right there. Right there. So right there. Then the next set of instructions are increment. And we can increment anything we want. An increment means just simply add 1 to it. Increment 1, A is equal to A plus 1. Increment R0, R0 is equal to R0 plus 1. Increment P1, P1 is equal to P1 plus 1. We add 1 to P1, whatever was there. Increment location pointed to by RI, which I'm not going to get into that one there. That's one that's in that indirect. And then along with increment, we've got decrement. Decrement A, decrement R0, decrement R5, whatever. Decrement memory location 35, right there. So we can decrement those. And then we've got the multiplies, and I'll talk a little bit more of those right there. We got a multiply and divide right there. And then we've got one here, decimal adjust, which we'll talk about here in a second as I go through the slides right there. So, later on. Yeah, the multiply is a little bit tricky because multiply, we're going to be storing our results in various places. The results get stored in the registers right there. Because if you multiply two 8-bit numbers, you're going to end up with a 16-bit number right there. So, okay, we have our logical right there. We got AND, OR, XOR, and clear, and complement, and then rotate right there. I'm not going to go through these in too much there, but for example, if we want to do an OR, if I want to set a bit, for example, right here, OR logical. If I do OR logical right there, and I'm going to say P1 mode out right there, 0, 1 hex right there. What that does is 0, 1 hex is 0, 0, 0, 0, 0, 0, 0, 1, right? We don't care what these are. They're going to be left alone, but this one will always be set. That sets that bit is what that does. It makes that bit always a 1. If I want to clear something, I might use an AND right there if I want to clear a bit. For example, if I want to clear that bit, I could do a ANL port 1 mode out, FE, there should be a number sign there, number sign 0 FE, X, I forgot the number sign there because it's immediate data right there. So if I do this, that's going to clear that bit because let's say, for example, this is port 1 mode out, and it's got 1101 1111. It's got in there, and then I do the command ANL port 1 mode out, and I do number sign 0 FE right there. Well, FE is 1111 1110, right? These bits are left alone. They're not changed because right there. So if they're a 0, they remain a 0. If they're a 1, they remain a 0. But this bit is now set to a 0. I clear that bit right there. That's what I've done there. There is I've cleared that bit. If I want to set that bit, I would do a OR L port 1 mode out, number sign 0 1 hex. That would set the bit. So this clears that bit. This sets that bit. So I use the OR to set the bit. I OR it with a 1 wherever I want to set a bit, and I AND it with a 0 wherever I want to clear a bit. Now, as it turns out, many of the bits that we're going to be setting and clearing, we can address one at a time, and we don't have to use the AND and the OR. We can use commands like clear and set bit right there. But some registers we can't do that with that there, so we have to do it this way. And if we go back to our code right here, notice that right here, that's exactly what I'm doing with these commands right there. That is clear. Setting those bits is what that's doing. I'm setting that bit there. I'm doing a logical OR with port 1 mode in, number sign 0 1. So I'm setting that bit to a 1. I'm doing a logical OR with P1 mode out, number sign 01 hex. I'm setting that bit. Later on, we'll look at that port and see what we're doing there. That's there. So here we're clearing a bit right here. This is a bit that we're clearing, and that happens to be green LED is a bit addressable. A bit. I don't have to use the AND function. That's there. See, some memory locations we can address bit by bit. Some we have to address the whole word. That's part of what makes life interesting. Why we have to understand the processor we're working with. Up here, we have this line right here. The green LED is port 1.0. That means it's port 1, whatever memory location is, .0 is the 0 bit in that word. So I can here clear that bit with just the clear command. Yeah. OR what? L. Logical OR. OR logical. Now, it's not logical that the L is at the end though. But it's a logical OR. We're doing a OR bit by bit. And same thing with AND, ANL. Right there. And CPL is complement. If it's a 1, it's down a 0. So it inverts it, toggles it. So ORL is clear logical. Logical clear. And it shows it right here. This slide actually explains it there a little bit right there. Unfortunately, your screen cuts off where it says NALA and ORL. Yeah, the screen cuts it off here. If I I don't have a white right there. You can see that it says ANL there and ORL there, right? The screen cuts it off there. So, but what this is saying is that I'm going to mask bit 2. That I'm going to that there. Now, this particular case, that may be followed with a jump not 0. So again, that's quite often we'll do a logical and we're looking for if a bit is set. Because what this will do is this will AND it with bit 1. So everything else in the accumulator other than bit 1 is going to be a 0. That's there. So if bit 1 is a 0, if my next command is jump not 0 or jump 0, it will look at the 0 flag. That's there. So this is looking for that bit. We're masking that bit there. This particular case, we're going to do a OR with the accumulator. That's there. ORs are usually used to set a bit. ANDs are used to clear a bit or to test for a bit or look for a bit to see if it's set. And again, we're going to see these in examples. We're going to use them. That's there. So you may not understand them 100% after today. This is getting into the really nasty part of this compiler right there. Okay, can I go on to the next? And again, as we go through here, we've also got the XOR. I'm not going to cover the XOR. That's bit by bit. Right there. XORs are quite often used if you want to complement information right there. Right there. So, clear, complement, rotate, and we won't talk about rotate, but rotating, if you rotate right or left, is the way of multiplying by 2 actually. But there's other places where we'll want to rotate right or left. And then swap nibbles. There's times when we want to swap the high order byte with the low order byte. There are times that there. These are the instructions. How we use the instructions, we'll see as we do examples. That's there. The next set of instructions we've already talked about a little bit. The move, right there. Now we've got two instructions here called move C, and that is using encode memory. I need to come back and talk a little bit about the memory structure of this. I really didn't get into the memory structure too much, in the fact that this has got code memory, and it's got data memory, and it's got external memory. There's three different types of memory for this processor. I remember I talked about it briefly there, but this is where this becomes important, because we've got instructions here for external memory and instructions here for this. This is regular data memory right there. That's only location 00 to FF. We only have 256 bytes of internal memory. This is our code memory, and anything in code memory, I should point out, is part of our code right there. We have to write it and set and define that in the code. And this is our external RAM right there. So we've got three different memory locations right there that we can move data in and out of. When do we use them? It depends on the program. We're not going to get into them today. Push and pop deal with the stack. We'll talk about that later. Push and pop deal with the stack. Push and pop. That's a location memory where we can store information temporarily and pop it back off. That's used usually when we do function calls and interrupts right there. And then we've got exchange right there. These here are just simply, we're exchanging that there. Now exchange just means exactly what it is. Exchange A with R0, we move whatever was in R0 into A, and whatever was in A gets moved to R0 right there. And again, we can do that with direct memory, and we can do that with indirect memory. We can't do it with immediate data, because you can't move something into immediate data right there. And then we can exchange low order digits, which is kind of a funky one. We won't get into that at all today. The Boolean, these are bit by bit right there. Now these are Boolean. The previous one, let me kind of go back to our previous one right here, logical. These are byte-wide instructions, and they do it bit by bit right there. We look at these. This is clear C. This clears the carry bit. That's in that there. If there was a carry, that clears it right there. Clear a particular bit right there. Clear P1.0. Set bit. Set P1.0. In other words, turn it on. That there. Complement C. Complement P1 green LED. So these can only be used on instructions that can be set bit by bit, or memory locations. Not every memory location can be set bit by bit, right there. So we can do things by bit. And notice that there's also a couple of move commands here and a couple of logicals set there. Now the other ones we've got here are the jump if C is set, jump if no carry, jump if specified bit is set. Right there. So I could do a jump P1.0 comma, some function call, whatever, right there. Do next, right there. So in other words, I can look at a particular port at a particular bit on the port, and I can check to see if a button's been pressed. If a button's been pressed, then I can jump over a piece of code. If that button's not pressed, I don't jump over the code. So I can look at input ports one by one. These are actually fairly powerful. That there. This here is, if a particular bit is set, you clear it and then jump. That there. So in other words, if you have an overflow flag, for example, that there, you can that there. Well, again, we'll see some of these examples. We're out there, and then our last set of here, right there, is we have our A call that calls a subroutine, a long call. This is a return from some return from interrupt. We'll see examples of that. This is an absolute jump, a long jump, and a short jump. And this is a short indirect, which we won't use too often. This is a jump if 0, jump if not 0. This is compare and jump if not equal. We can compare the accumulator or two registers together and do a jump. Do a jump if they're equal to each other or not equal to each other. I guess if not equal, we only have to not jump and compare and jump if not equal. We don't have a jump if equal. And then we have the decrement and jump if not 0. We've already talked about that one there. And then our last one is no operations, do nothing. Right there. And that's where I'm going to stop today. That's there. There's a lot of instructions. We're going to come back and see them. That's there. Like I said, we're going to be meeting tomorrow, right? Yeah. As a full group. So I'll go through tomorrow. I'll go through some examples, and then next Monday we will actually come in and you'll do the examples. That's there. So that's there. Most of these instructions make more sense when you see them in operation. Seeing them in a list here is just out there. But when we actually see me going through step by step and you watch the data move back and forth, that's there. And I probably won't write up a lab. I'll probably just have a set of instructions where I do a bunch of things tomorrow there with a board without a script or anything. I'll just make them up and do them as I go along and try each of these instructions and let you look at that. Remember, the debugger allows us to stop and look at these one at a time right there. So, and we could look at all the registers, so we could do the jump or that there, and we could see where we go in the code that there. So that's really the easiest way to see how these instructions work. So with that said, I'm going to stop, and I told the other class, and I'm going to